Hello and welcome to another power system analysis class. As I have sent an announcement before, we're going to have an exam this week. And before the exam, I have prepared some solved problems for our review session. The exam questions are going to be very similar to these questions. I may just change a few numbers. And on top of that, you're going to have some theory questions as well. So without further ado, let's jump into this. By the way, the exam this week would be the admittance bus, per unit transformers and transmission lines. These are the topics that we will be covering. Everything after that we taught after the first exam would be included in the second exam. And the final exam would be a comprehensive exam. So everything would be included. So without further ado, let's start. Again, you're already familiar with the way the review sessions work. I will give you questions. I will give you a few minutes to solve it. If you are able to solve it, you're going to get bonus points for your upcoming exam. The first problem is we want to build a Y bus for a 3-bus system. Z12 is J.2, Z13 is J.4, and Z23 is J.25 per unit. They have no shunt bus. And again, we want to build the Y bus for a 3-bus system. And if you need papers, sorry, it's the papers. No, this is just for you to solve for the review session. But if you're able to solve it, I will give you bonus points for the upcoming exam. Yes. For the online students, if you don't want to wait, you can skip this part and get to the results. But I would encourage you to try to solve it on your own. Use this time to solve it. It's going to help you a lot. I have a paper if you want to solve the review session problem. Again, if you solve it, you're going to get bonus points on your upcoming exam. Okay, did you solve it? Let me start with the first one. So we want to find the admittance matrix, but all we have been given is the admittance. Instead of the admittance is the impedance. So we have to first convert the impedance to admittance. First impedance that we have is Z12. So to find Y12 is going to be equal to 1 over Z12, which would be equal to 1 over J.2, which gives us negative J.5 per unit. Now the same thing for Y13 is going to be equal to 1 over J.4, which gives us negative J2.5, again, per unit. And the same thing for Y23. It's going to be 1 over Z23. So it's going to be 1 over J.25, which would be equal to negative J4 per unit. Now that we have found Y12, Y13, and Y23, we need to find Y11, or the self-admittances, which is going to be Y12 plus Y13. So everything that is connected to bus number 1, which would be negative J5 plus negative J2.5. Both of them are per unit, so it gives us negative J7.5 per unit. Now Y22 is all the admittances connected to bus number 2, which are Y12 and Y23. Y12 plus Y23, which would be again negative J5 plus negative J4, gives us negative J9 per unit. And finally, Y33 is all the admittances connected to bus number 3. So Y13 plus Y23, negative J2.5 plus negative J4, which would be equal to negative J6.5 per unit. Now, let's insert another table. Then we have to find Y21, and Y12 is equal to Y21, which would be equal to positive J five per unit. Same thing for Y13 is plus J 2.5. and y32 would be equal to positive j 4.0. Now the y-bar matrix will look like this. We have negative j 7.5, positive j 5, positive j 2.5, and again, everything off diagonal it's a symmetrical. So positive j5 again, this is negative 9j and positive j4. Again, positive j 2.5, positive j4, and negative j 6.5. So if we add a shunt impedance, the shunt impedance would only affect the diagonal terms at the connected buses, and all off diagonals would be unchanged. The reason is because when you connect a shunt, that shunt is connected to a bus and a ground. It's not shared between two buses. Therefore, the off diagonals would not be changed. And the diagonal ones, just the self-admittances, those would be changed. So if in the exam I add a shunt, just remember that. Did you write this? Can I go to the second question? Again, the problems in the exam are going to be the same. I just would change the numbers. Now, problem number 2, a 138 kilovolt line has an impedance of 15 plus J40 ohms. We want to convert it to per unit. SB is 100 megavolt amp and VB is 138 kilovolts. And you can use your notes. Did you solve it? What is the answer? Yes, perfect. Remind me to give you um, bonus points. So first we have to compute the impedance base. For that, the base impedance base would be V base square over S base, which would be equal to 138 kilovolts. So it's 10 to the power of 3 and the power of 2 over 100 megavolt amps. So 100 times 10 to the power of 6, which gives us 190.44 ohms. So this is our impedance base. Now we have to divide the actual base. So Z per unit would be equal to Z of the actual divided by Z base, which gives us 15 plus J 40 divided by 190.44, which gives us 0.0787. This is what I calculated. If you round it up, that's perfectly fine as well. Plus J 21.21 per unit. Okay. Can I go to the next question? Yeah. So first you compute the impedance base, and then you divide all the actual impedances by that impedance base. Can I move on to the, okay. Now next question, a three-phase load draws 90 plus J45 megavolt amps at V load to load of 115 kilovolts. We want to express load current in per unit. S base is 100 megavolt amp and V base is 115 kilovolts. One extra paper to solve. Okay, did you solve it? Do you want me to solve? Or you need more time? Baby, 0.9 plus what? We just want the load current. Load current cause doesn't have imaginary parts. So I base is going to be equal to, first we want to find the current base, which is going to be the apparent power base over square root of 3 V of base line to line, which gives us 100 megavolt amps, so times 10 to the power of 6, divided by 1.732, which is square root of 3, times 115 kilovolts, so times 10 to the power of 3, which gives us 502 amps. Now, the per unit power, apparent power, this is the load power in per unit. So load power in per unit. The first one was the current base. Which is going to be equal to 90 plus J45 divided by the 100 gives us 0.9 plus J.45 per unit. Now, the magnitude of that is square root of 0.9 plus square root of 0.45 in the power of 2, which gives us 1.006 per unit. Again, which is square root of 9 squared plus 0.45 squared. Now, we have to find the current per unit. The current per unit, which would be equal to the magnitude of the apparent power per unit over the voltage per unit, which gives us 1.006. Would be 1.006 per unit. Now, the actual value, so A actual would be what? Would be the per unit times what? Times the current base, which is 502, which gives us 505 amps. Can I go to the next question? Yes. Okay. Again, a current doesn't have an imaginary part, so you have to find the magnitude and then the magnitudes. You want to find just the magnitude. You don't want to find the angle. And we were wanting to find us the value of that. Now, next problem, we have a 25 megavolt amp, 69 with 13.8 kilovolt. So the primary is 69, the secondary is 13.8 kilovolt transformer. The open circuit test, we have 50 amps and 40 kilowatts. For the short circuit test, we have 1600 volts and 200 kilowatts. We want to find the RE, XE, RC, and XM. So the internal resistance, admittance, reactance, and the loss in the system, the loss in the core, XM of the core, and so on. We already learned to determine the internal parameters of a transformer. We need to do two tests, the open circuit test and the short circuit test. And if you remember, for each test, we had different voltages. And for using those tests, we can determine the internal resistance, the internal reactance, and so on. The core loss and so on, magnetic loss. You can again use your notes. You need more time? Tyler, did you solve? Okay, let's see. Solve it. So first thing, I of short circuit is going to be 25 times 10 to the power of 6. It's 25 megavolt amps divided by 69 times 10 to the power of 3, because we want to find it at the high voltage side, which is 69 kilovolts. And this would be 362.3 amps. So it's going to be the rated apparent power over the high voltage side voltage. Now, the impedance is going to be 1600 over 362.3, which gives us 4.41 ohms. It's actually 4.416 ohms. So we have found the impedance. Now, what is the impedance? Yes, RE plus XE, yes, or JXE. Am I correct? In other words, the magnitude of Z is going to be square root of RE squared plus XE squared. Am I correct? Or in other words, XE would be square root of Z square minus R square. So if I want to find RE, it would be P of short circuit, the real power, over I short circuit in the power of 2. So what is the real power that we have? How much is the real power? 200 kilowatts. So it's going to be 200 times 10 to the power of 3, because it's in kilowatts, over 362.3 in a power of 2, which gives us 1.52 ohms. So we have the resistance, RE. Now we have to find the inductance, or the imaginary part, XE, which would be square root of C square minus RE square, which gives us square root of 4.416 square minus 1.52 square, gives us 4.15 ohms. So we found RE and we found XE. Now, this was for the short circuit test. Now from open circuit test, for the high voltage side, I'm going to call it the open circuit. So RC is going to be V of high voltage in a power of 2 divided by P of open circuit, which gives us 69 times 10 to the power of 3 in a power of 2 divided by, what was the power? It was 40 kilowatts for open circuit. So 40 kilowatts, so times 10 to the power of 3. This gives us 119 mega ohms. It's going to be 69 times 10 to the power of 6 divided by 10 to the power of 40 times 10 to the power of 3. So. Now this is a huge resistance, and because it's a huge resistance, it's often neglected because no current would pass this when it's in parallel. It's like an open circuit, as mentioned. Now Z of the core, which is going to be V of high voltage divided by I open circuit, gives us 69 times 10 to the power of 3 divided by 50, which is going to be 1,380 ohms. Therefore, X ohm would be almost equal to 1,380 ohms. Why? Because when this is in parallel with 119 mega ohms, this is much smaller, so the equivalent would be very close to the smaller impedance, which is in parallel. Does it make sense? And all of these are referred to the high voltage. So RE, answer RE would be 1.52 ohms. XE was 4.15 if you want to round it. And RC is equal to 119 mega ohms. And XM is equal to 1,380. Do you want me to go to the previous slide if you didn't? Did you take the notes for the previous slide? Yes? This one? Okay. Can I go to the next question or? Okay. Next question. A lossless 345 kilovolt line with an X of 55 ohms. Both terminal voltages are 1 per unit. We want to find A, the P max, and B, the P at delta equal to 20 degrees. So this is a power transfer in transmission lines question, if you are. And again, we want to find P max and P. Again, your exam is going to be in the next class. These are review questions, if you haven't noticed yet, for those who just arrived. And the questions are going to be very similar to these. It's going to be the same format as your previous exam. For the online students, I've already posted an announcement for them. Their exam is going to be this weekend. So we won't post a video next class when you have an exam.
Those the questions.
Yes, I would post the video again on the YouTube channel. You already have the link, so you can go to the YouTube channel and you can find all the videos. Yes, yes, yes. I'll try to finish. Even if I don't, the ones that I finish would be in the exam. Okay. Did you solve it? So first thing that we need to do, we have to convert the reactants to per unit. So base is going to be 345 45 and by the way, SB is 100 megavolt amp and VB is 345 kilovolt. So it's going to 345 in the power of 2 divided by 100 gives us 1,190.25 ohms. Now, reactance per unit is going to be 55 divided by 1,190.25 gives us 0.0462 per unit. So the maximum power occurs when, again, as you remember, delta. So maximum power is when delta is equal to 90 degrees. And P is going to be equal to V1, V2 divided by X. So P max would be equal to V1, magnitude of V1, V2 divided by X, which gives us 1 divided by 0.462, which gives us 21.66 per unit. Or if I want to multiply by 100, the base, it's going to be 2166 megawatts. If we want to find the actual, but just the per unit is enough. So it's going to 21.66. Now, if we want to find P at a delta of 90 degrees, 20 degrees, it's going to be equal to 21.66 times sine of 20 degrees, which gives us 7.4. Sine of 20 degrees is 0.34. So it's going to be 7.4 per unit. In other words, it's going to be equal to 740 megawatts. So you can see it's a huge difference when we have the maximum compared when we delta is going from 90 degrees to 20 degrees. Okay, I think we have only time for another one, and I'm going to solve this one because it's a more important one. A two-bus system has a Z of 0.03 plus J 0.04, and YC over 2 is 0.1 J. And given Y, V is 1 with the degree of 0 degrees and 0.95 with the degree of negative 5 degrees. This is the Y matrix, by the way. We want to find I1, I2, S1, and S2. Again, this is a Y bus. problem, we want to solve for the currents and power. Do you remember if we had either the current and voltage, or we had PQ or PI or VI system? This is from that lecture part. This one I'll give you 3 minutes because we're running out of time, 5 minutes actually, and then I would start solving it. Now, this is the exact example that we had from the lecture, and I'm just getting that, lecture question that we had. And I'm just going to put on the Y bus. I'm going to just mention here to make your job a little easier. Y bus and faster would be equal to 12 minus J 15.9. And this is actually the last question that we solved the other day. 12 plus J 16. And again, negative 12 plus J 16. And 12 minus J 15. And I would recommend that you go back and revisit this example. Okay, we have to find the voltage in a rectangular form. We can do both actually, but rectangular form is going to be easier. So 1 with a degree of 0 degrees is equal to 1 plus J 0. And V2 would be equal to, if we convert 0.95 with a degree of -5 degrees, it's going to be equal to 0.9466 minus J 0.0827. Now, if you want to find I1, it's going to be equal to Y11 V1 plus Y12 V2, which would be equal to 1.63 plus J 0.569 per unit. Again, as you know, I is equal to YV. And if I want to find I2, would be equal to Y21 V1 plus Y22 V2, which would be equal to negative 1.635 minus J.49, sorry, J.49449 per unit. Now, the complex power or the apparent power S1 is going to be V1 times I1 conjugate, which would be equal to 1 times 1.634 minus J 569, which gives us 1.634 minus J 569 per unit. Now, same way we can find S2, and S2 would be equal to, I'm just going to write down the actual value. It's going to be 154. This is what I calculated. You can double check it later because we don't have enough time. I'm going to give you the final answer. 154.8 megawatts minus J 29 megavolt amp reactive. So this is the generation. This is the consumption, the consuming part. And as you can know, it's if you want to find the first ones, you just multiply by 100. It's going to be 1,000. 163.4 minus 5.69 for the actual one. Okay, so we run out of time. Thank you so much. If you have any questions, just please email me, and good luck on your upcoming exam. Thank you.